Hello everyone and welcome back to the channel. In today's video we are going to build a complete Simulink simulation of a pendulum mathematical model. If you haven't seen the previous video where I explained the equations and derived the model, I recommend watching that first. It will help everything make more sense. To begin, open MATLAB first, go to the command window and simply type Simulink. Press enter and choose the blank model. This opens the main Simulink workspace where we will assemble the blocks needed to simulate our pendulum system. The mathematical model we are simulating consists of 4 states described by 4 ODEs. These come directly from the previous derivation and include pendulum angle alpha, angular velocity omega, cart position x, or here x2, cart velocity v. We will use Simulink to numerically solve these 4 differential equations. To implement the equations, we will use MATLAB Function block. Open library browser. Go to user-defined function. Drag MATLAB function block into the model. This block allows us to write MATLAB code directly inside the Simulink. Double-click the block to open it. You will see a default function with inputs u and output y. Delete the default content and rename the function to something meaningful, such as pendulum model. Inside the function block, the input is the control force F with state X. The outputs will be the 4 differentials equations: d alpha, d omega, dx, dv. We also define the 4 states. Alpha equal x1, the pendulum angle, W equal x2, the angular velocity, which is omega, x position of the cart, x3, v equal x4, velocity of the cart. Next, we write the system parameters: M1, M2, L, KT, and G, and assign their values, numerical values, inside the function block. Now enter the 4 ODEs exactly as derived. Use clear variable names that match your equations. This is the first differential equation, d alpha equal omega. Here is W, dw, d omega, and these are the same equations as derived here. Now we will save the function and return to the Simulink model. We'll choose this name. Each ODE must be integrated to get the corresponding state. We do this using the integrator block. Go to library browser, continuous, drag integrator block. Control and left mouse button to do copy paste. Name each integrator according to the state it represents. Here is alpha, omega, x, and v. Double-click each integrator to set initial values. Assume the pendulum state is alpha 15 degrees. We will convert it to radian. Here is 0, we'll put 15 degrees, multiply by pi. Each of the rest states equals 0, omega, x, and v. The MATLAB function block requires the states as a single vector input. To organize the signals, use a mux block to combine the four state outputs into one vector. We commonly used block and use mux. Here we will put 4, apply, feed this vector into the function block. This keeps the block diagram clean and organized. To supply the external control force, go to Dashboard and drag knob block. We can't connect the knob block directly to F. We use constant block. We name it as F and double-click the knob. We select we drop the constant block here and select. We choose the maximum and minimum. Minimum is -10, maximum 10, and click apply. Since we are running an open loop simulation, set the constant block to 0. Open model configuration parameters. We'll go to modeling, model settings. Choose the start time 0, stop time 15 seconds. We select a solver type fixed step and solver method range quota 4. Step size 0.1. Click apply, OK. To view the state trajectories, go to sinks and drag scope block. Set the scope to have 4 input ports. Settings. Scope settings. Number of input ports 4. OK. Now connect each state output to the scope. We also change the layout of the scope, display grid, so that, and the setting, axis, style, white, display legend, show legend. Now save the model and click run. Open the scope to visualize. Here is the pendulum angle and angular velocity, cart position, and cart velocity. To make legend appear, we have to put here the names alpha, omega, x, v, and rerun alpha, omega, x, v. You should see a natural oscillatory response since no control is applied. If you increase the simulation time for 40 seconds, for example, you'll observe how the oscillations gradually decay. We put here 14, 40. In this video, we learn how to build a Simulink model of the pendulum system, implement ODEs using MATLAB function block, integrate the equations, set initial conditions, configure the solver, visualize all states using scope. This workflow can be extended to simulate many other dynamical systems using Simulink. Thanks for watching, and I will see you in the next video.